Well, how's everybody doing out there? Well, welcome to day 15 of Corona Online School. So today we're actually moving on to chapter 8. And so in this case, this is still going to build off of what we've been learning in chapter 6 and 7. So we want to keep all that stuff in mind. So again, the big driving force behind what we're using in chapter 8 is this ability to use the central limit theorem to make normal curves by looking at the means of the means basically. So in this case, what we want to do is try to get actually better estimates for the population mean. So in this case, we'd like to know what the population mean is, and without again being able to sample every single element, or every single data point, it's pretty much impossible to get the exact population mean. Now we know we can use the sample mean as a way to estimate the population mean, and I kind of mentioned that in this section. This is what's called the point estimate of the population mean. But the downside is by saying, like the sample mean is this, so I assume that means the population mean is the same thing, isn't necessarily true and doesn't necessarily give us a lot of confidence. So our goal is what we want to do is try to create what's called a confidence interval that gives us a small interval that estimates that the population mean will be somewhere in between these two values of the interval. And so the cool thing is that we can actually kind of increase our percentage of how accurate we think we are. And so we'll talk a little bit about that later, but like ultimately, like this little example at the beginning talked about iPhone cases and stuff like that and how feasible it would be to like measure them. And so it'd be tricky. And so, but if we could get some kind of confidence, like 95% confidence that we know the population mean is between two values, then that gives us something to work with, and it gives us something, that we can kind of, write home about basically. So there's a bunch of little definitions here in the beginning, so I'll just go through them real quick. So again, the point estimate is going to be a number that estimates the parameter. So remember, parameter is always something that describes the population. So for this chapter, we're going to be talking about the population mean. So whenever we talk about parameter, it's always going to be population mean for this section, because that's the thing we want to know something about. And so our confidence interval is going to be this range of values in which we're trying to trap the population mean into. And it's kind of cool how it works. I mean, it's pretty powerful and it's actually really accurate, which is kind of nice. So, and that's one of the reasons it's used more than just one sample mean, for example. Because again, we're going to be using the central limit theorem to take a bunch of different samples. And so it's going to guarantee us with pretty strong certainty that our population mean is going to fall within this range of values, which is kind of cool. And so I mentioned here that, you could talk about confidence intervals that are less than 90%, but again, that doesn't give you a lot of confidence. I mean, it would be more like an unconfidence interval at that point. So typically, they're always going to be at least 90%, but in most cases, like the two really popular ones are 95% and 99%. So, and that means is that basically means I'm 95% confident that the population mean is going to live in between these two values, or even better yet, I'm 99% confident. So basically, there's like a 1% chance that the population mean isn't going to land in that interval. That's the way this is actually going to work. So that's pretty strong. That's a pretty powerful statement to be able to say there's only a 1% chance that we, basically messed up and the mean isn't in there. And so that's kind of what this statement says here. So, like, if you were the boss of this company and someone came to you and said, I think the average width of our iPhone case is 67 millimeters, is that satisfying, or does this sound more satisfying? I'm 95% confident that the average width of our iPhone cases is between 66.8 and 67.2. So there's not that much difference number-wise, like 67 is in both of them, but giving us this little bit of range allows that there could be an error, because we know like the widths of them could be slightly off by a little bit, just like the same thing when we were doing our M&M counting. Like if we'd got to count the M&Ms, like every bag of M&Ms doesn't contain the exact same number of brown. Like there's a range that you're going to hit, and so that's what this confidence interval does. It gives us a nice little range to kind of ensure that our mean is in there, but it allows for a little bit of flexibility. All right. So two other quick definitions here real quick. So our degree of confidence is the probability 1 minus alpha. So in this case, so like the 95% would tell us that our alpha is 0.05 in this case, and that's where we're getting our 95% confidence from. Or if our alpha was 0.01, that would give us our 99% confidence interval in that case. So the alpha we'll see in a little bit is going to come in when we talk about this critical value in the next step. So if you see there's an alpha down in the very next definition. So, but basically it's just telling us whether we're using a 90%, 95%, 92%, whatever the confidence interval is. And then I'll show you graphically where the alpha shows up on our normal curve. So just kind of keep that in mind. We don't necessarily have to memorize these definitions or anything, but and so finally, our critical value is the number that's on the borderline. So it's going to be our extreme values that our population mean is living in between. And these numbers are actually going to be z-scores so that we're going to come up with. So in this case, our z alpha over 2 is the z-score that we're interested in that separates the area of these normal curves. So again, it'll make more sense when you see the picture of it and stuff. All right, so let's move on. There's a little bit of stuff before we get to the actual practice here so far. But so to construct a confidence interval, so we basically have to make a couple of assumptions. So the first one is that our sample is a simple random sample. And so I wrote this down, but in reality I shouldn't have even had to write it down because if we're doing statistics that's not a simple random sample, then it's just silly to begin with. So if our sample isn't random, if it's not simple, then really all the statistics that we get from it are invalid anyway. So, but I put it down there just to make sure you know it's there. So the next thing is we need to know the population standard deviation. And so that's kind of weird because we're not always likely to be able to know the population standard deviation. So there are ways you can get around it. You can use some estimates and stuff like that. But in the next section, we'll see how you kind of deal with if you don't have the population standard deviation, because it's kind of weird if you have the population standard deviation but not the mean. Kind of an oddball thing to happen, but it is possible. And then the last thing that's most important is the population either has to be normally distributed or our sample size has to be bigger than 30. And so remember, the cool thing is if our sample size is bigger than 30, then we can use our central limit theorem to turn it into a normal distribution. And so, so even though the original data wasn't normal, we can use it to be normal. All right. So in this case, so this is a little picture of what the 95% confidence interval looks like. And so if you remember, our empirical rule talked about that also. And so that's why we've got z-scores of -2 and +2 here, because those are our z-scores for 95%. And so when we're calculating this, what that means is this white area, if you add them together, since all probabilities add up to 100, means that we're going to have 5% that lives in that white area. But since it's divided between the two spots, we'd have to divide that in half. So that tells us that we've got 2.5% above and 2.5% below when we're talking about our confidence interval. So this would be our alpha in this case. So our alpha would be the 0.05. And the reason that we denote that z as alpha over 2 is because what we're doing is we're taking the alpha, we're dividing it by 2 to figure out what the probability is in the upper and lower sections of these guys. So we want to be careful when we say it's at 95%, it doesn't mean that there's 5% on each side. It means what's left over adds up to 5%. So in reality, there's 2.5% above and 2.5% below that we could mess up in this case. So our population mean, if it happened to land up here, then that would be bad. It didn't land in the blue spot. And that would be, we'd fall into that, 5% that we messed up. There was a chance that we messed up. But anyway, so let's go on. Let's try some actual problems here. So enough talking for now. So what we want to do is build a little confidence interval, just basic, like this isn't a fancy problem or anything like that. So they've given us our sample mean, and they've given us our sigma equals square root of n. So this is our normal curve standard standard deviation that we're working with. And the goal is we want a 95% confidence interval for the population mean in this case. So what we're going to do to actually calculate this population mean would be the same thing if we were doing like z-scores and stuff like that. So we want to start with our 23. It's always going to be in the middle. And then what we would do is we would add, 2 times the standard deviation to that value. So in this case, we're going to get 2 times, because we're using 95 confidence interval, this means our z is 2 and negative 2. And then we're going to multiply it by our sigma square root of n in this case. So in this case, we get 23 plus 2 times 1.5. And if I multiply 2 times 1.5, that gives me 3. So in this case, my upper bound, so this is going to be my upper bound for my confidence interval that I'm building. So now I want to do the exact same thing, but in this case, subtract 2 times the standard deviation. So 23 minus 2 times 1.5 equals 23 minus 3. So this gives me a 20. So this is going to be my lower bound for my confidence interval. So what this is saying is that my population mean, I'm 95% confident that my population mean is somewhere between 20 and 26. And so you'll see this written a couple different ways. So sometimes you'll see it written in interval notation, where you use parentheses. For me, I like the inequality notation a little bit better. So for me, it would look like 20 less than. And so we put our mu in there, because again, the goal is we're trying to estimate the population mean. And so we want to put our mu in there, not our sample in there, even though our sample mean is in there. And we centered this, this interval around our sample mean. The goal is we're trying to estimate the population mean. So we want to put the population mean parameter in there. So it would look like it's 20 less than mu less than 26. And so again, I like using the mu or the inequality notation, because this way I know what I'm trying to estimate. If I just look at this interval, that could be anything to me. I mean, theoretically, it could be an ordered pair, it could be an interval, but there's nothing tying it to the mean. So that's one of the reasons I'm not a big fan of the interval notation. Books do use it and stuff like that, but for me, I'm going to usually write this notation better, just because, again, I know exactly what I'm trying to estimate in that case. So, all right. Is that okay, everybody, looking at that? All right, perfect. So in this case, just kind of like summarizing what I did. So to find a confidence interval by hand, which is what I did here, so no calculator or anything, there's a couple things that we need to know. So we need to know the point estimate, which in this case was the sample mean. So we need to know our sample mean. So we need to find the standard deviation or have it given to us. So in this case, our standard deviation was given to us. It was that 1.5 that we had. And then we have to find the z value that corresponds to that confidence level. So this is where it can get a little tricky, because pretty much the only nice values that we have are based on the empirical rule, are 68, which we would never want to do a 68% confidence level, because that's basically not confident at all. 95, which turns in, that's handy, so we can do that one. And then 99.7, which is fine too, but that's almost overly confident. You might as well go up to 100%, at that point. So you'll have problems where you'll have 95, 92, 94. There's all kinds of different ones just to test it out. So the goal is we'll have to figure out, how do we actually figure out what the confidence level is, or how do we figure out what the z-score is for these confidence levels? And so I'll show you that in a minute. But so again, just to kind of summarize, here's what our confidence interval would look like. So I just broke it up into 2 separate instead of writing it with the plus minus. So I wrote mine as x plus z alpha over 2 sigma square root of n, and then x minus z alpha over 2 sigma over square root of n, instead of writing it with the plus minus notation. And then this is exactly how I wrote it out. It doesn't look this complicated because my z alpha and all that stuff was just a single number, so it didn't look quite as overwhelming. But that's exactly what I did when I wrote mine out. And so just to make it look a little bit cleaner, this z alpha over 2 times the standard deviation is actually what's called the margin of error of the problem. So it's, it's that a little bit of plus or minus that we're allowed to have. So that gives us, so a little bit of wiggle room to make sure that our population standard deviation or population mean actually falls in our interval. So a lot of times you'll see it denoted just as plain old E, and then your interval looks like this, which is a much cleaner looking thing than all this Z alpha, sigmas, square roots of n, and all that stuff. So, but it all means the same thing. So in the end, but all right. So let's figure out how we actually find the Z alpha over 2. So the good thing is you may not know it already. You already know how to do this. It's just me explaining to you how to do it. So in this case, let's say instead of doing a 95% confidence interval, which we just did, what if we wanted to do a 90% confidence interval instead? What would those z-scores actually look like? Well, again, the main thing we need to do is we have to figure out kind of what this alpha is on the upper end and the lower end. So again, if I do 1 minus 0.90, then that tells me that 10% of the data lives in this blue part. These two blue parts, technically. So 10% lives in these two areas combined. But again, since I've got an upper half and a lower half, then that means I need to divide this by 2. So each of these guys are actually 0.05 or 5%. So I've got a 5% chance of falling, not inside my confidence interval on the upper end. I got a 5% chance of falling out of my confidence interval on the lower end. So I got a 10% chance of missing the confidence interval altogether. But the reason this is going to come in handy is because I know something about normal curves, and I know that their probabilities, like the area under the curve is the same thing as the probability. So in this case, if I choose this as my, that's the z value I'm trying to figure out, then if I go here and shade all of this area in, then that tells me from here the whole way up to here is 95%. So what I can do is I can actually use inverse norm, 0.95, and in this case we're using the standard normal distribution because I just want to figure out what the z-score is. So I'm going to have a 0 mean and a 1 standard deviation. I can just throw that in the calculator, and that's going to give me that exact z-score that would allow me to calculate the confidence interval that I'm looking for. So let's throw this in the calculator real quick just to see what we get. So again, inverse norm is under second vars. Inverse norm. So I want to do my area first at 0.95. And again, since this is a standard normal, I want 0 and 1 for my mean and standard deviation. And so in this case, I get 1.644. So usually with these, we kind of round them to 2 decimal places. So I'm going to leave this as 1.64 as my z-score. Let's see, where'd my picture go? Here we go. So in this case, I get 1.64. So that means this z-score is 1.64. And then since, again, this is the normal standard, this is just going to be negative 1.64 in this case. So we can do this with any value. So for example, if I go back to the calculator, what if we wanted to test, 95%, a 95% confidence interval? So I don't think I have you guys do that, do I? Let's see. Nope, I have you do 98. Good. So if I want to do a 95% confidence interval, so what value would I have to plug in here? So 95% confidence level. So in this case, again, I would take my 1 minus 0.95, gives me 0.05. Divide that by 2, gives me 0.025. And so in that case, that means I'd only have 0.025 on the upper end. So that would mean that I'd have 97.5% on the lowest end. So if I did inverse norm with 0.975, that's going to give me the z-score for a 95% confidence interval. So let's type this back in. Change this to a 7. And then hit enter. And so notice it's not exactly 2 like we say it is. So it's pretty close to 2, but in reality it's actually 1.96. So a lot of times you'll actually see 1.96 as the proper z-score for 95%, even though the empirical rule says it's approximately 2. So it's pretty close. I mean, it's not too far away, but in reality we should be using 1.96 for our actual 95% confidence interval. So in this case, our z would be 1.96 in this case. So keep track of these guys, because I think one of these problems coming up, here coming up, I've got you actually doing 90, 95, and 99. So we've seen already, so this should be 1.64. This will be 1.96 for 95. And then I'll have you guys test 99 on your own and figure out what you come up with for that critical value. That way you don't have to look them up every single time. So go ahead, I'll have you guys do practice 1 on your own here. So this is finding a 98% confidence level. So again, do the same thing I did from above. Figure out what the alpha is first. Divide the alpha by 2 to figure out the areas that are outside of our confidence interval. Use that to find the area under the curve. And then that'll give us our nice z-score for 98. All right. And then again, do 99 also, so that way you can kind of fill in the chart. And then I've got you doing the same thing like practice 2, practice 3. This is just kind of playing around a little bit with the rules and stuff. So try those on your own. See how you do. If you get stuck on anything, just kind of let me know. And then practice 4, 5, and 6. These are actual examples, like full blown. So again, try these guys on your own. Let me know if you have any questions or if you come up with any problems or anything like that. And then changing the confidence level. So basically this is just kind of showing what happens if you use the same sample mean, the same population standard deviation. What happens if we change our confidence level? So I don't want to give it away, but hopefully you'll think about, as the confidence goes up, the confidence interval should get smaller, because the goal is like to be 68% confident. I mean, like the interval could be super wide because, it's going to, it might miss a lot of stuff and things like that. So it has to get tighter and tighter to get more accurate in this case. So hopefully we'll see that when we do those. And then calculating the sample size. So let me work through this for you because this can be a little bit tricky. So the goal is, in this case, what if we kind of started off with a margin of error that we wanted, and then we want to work backwards and figure out, well, how big of a sample would I have to take in order to get this margin of error? So in this case, the population standard deviation for the age of students is 15 years. So that's going to be our sigma. And so if we want to be 95% confident that the sample mean age is within 2 years of the true population mean age of these students, how many randomly selected students must be surveyed in this case? So in this case, the E is 2. So we only want to be 2 years away from our thing. So the way it's going to work is we're going to have X equals, or mu is going to be so X plus E, which in this case is X plus 2. And then on this side, X minus E, which is the same thing as X minus 2. So in this case, we know our error is 2. We know our population standard deviation, but the problem is we don't know what our sigma is in this case. And we also know our z, technically. In this case, I'm going to cheat a little bit and use z to be 2 just to make the calculation a little bit easier, even though it should be 1.96. but I'll cheat a little bit just to make the math a little bit prettier. So in this case, if we did our formula, what we want to do is write down what E is equal to. So that's our Z alpha over 2 times sigma all over the square root of n. And so now you just kind of plug in what we know. So we know E is 2. We know our Z alpha, I said, was 2. Our sigma is 15. The problem is we don't know what n is, and it's in the denominator, and it's got a square root around it. So this is going to require a little bit of algebra on our part. So don't turn the camera off on me just yet. Be patient. So at this point, what we want to do is we have to solve this equation for n. So really the main thing is just trying to keep everything kind of straight. Don't get too messy with it or anything like that. So the first thing I would do to kind of clean this up a little bit is let's go ahead and multiply this 2z score by the 15. So this way we'll get 2 equals 30 over the square root of n. And so now what we've got is we've got a nice little fraction on each side. So if you remember, we can cross multiply these guys together to get rid of that fraction. So in this case, 2 times the square root of n is still going to be 2 square roots n. 1 times 30 is just going to be 30. And then from here, we're trying to get n by itself, but ultimately we need to get square root of n by itself first. So we can divide both sides by 2. And so now we're left with square root of n equals 15. And so now to get n by itself, we've got to get rid of that square root. So if you remember, if we square a square root, it cancels the square root out. So in this case, what we want to do is square both sides of this equation. So in this case, the square root and the square just disappear. So all we're left with is n equals, and then 15 times 15 is what, 225, I think? I think that's right. I better check just to make sure. Yep, 225. Good. All right. So in this case, in order to get this margin of error that we're looking for of just 2, plus or minus 2 on each side of the sample mean, then we'd actually have to survey 225 people to be able to do that. So it's kind of cool that, so you can do this multiple ways. So one way you could approach the problem is you could just go out and take a sample, take your chances, form your confidence interval based on whatever sample you make. It could be a big interval, it could be a small interval, it's hard to say. Or again, if you want certain requirements, it's like, okay, I need this to be only one, plus or minus 1, for example. I want it to be really, really tight, or I want it to be plus or minus 0.5. Then you can actually work backwards, figure out how big the sample would have to be in order to guarantee that we get the confidence interval that we're looking for, or at least the size of the confidence interval that we're looking for. So again, that's kind of cool. I don't think I had you guys practice any of these, but it's important to see that it is something that you can do with these guys. So if you want, ignore what I did, try to go back on your own and do it yourself just for practice. And so finally, the last thing in this section is, lo and behold, it turns out that there's actually a calculator feature that'll do all this for us. So not that anything's been super hard. I mean, the most intense thing we've had to do is be able to find the z-score. And then from there, all the math we did was all on our own with the calculator, or with just by hand pretty much. But it turns out that you can actually use your calculator to find this confidence interval without even, doing anything extra. You just basically type it in, you get the whole thing for you. So let me show you with this example how this would work. So in this case, we've got 11 old smartphones and these are all the prices for the different smartphones. And so again, this one's kind of these are always strange because, how do you know the population standard deviation without knowing the population mean? But again, that's kind of the nature of these problems. And again, we want a 95% confidence interval for these guys. So hopefully at this moment, you're kind of crying out going, whoa, wait a second. One major thing is missing here. I don't even have the sample mean at this point. So no sample mean. So if this problem was handed to you and you didn't know how to use this calculator trick I'm getting ready to show you, well, then you would just throw in all these data values into one var stats, calculate the sample mean, figure out what the z-score is for 95%, and just calculate it the way we did before. But the cool thing is the calculator actually allows us to do this without even knowing the sample mean. It'll actually find it for us, which is kind of cool. So, and I should have typed these into the calculator beforehand, so I'm going to end up going back and forth on these guys, but that's okay. So let me show you which command it is first, and I'll show you how to use it. So let's go to our calculator. So in this case, instead of going to the vars, we're actually going to go to stats, and we want to go to test in this case. And so the test that we're looking for is what's called, it's not a test, it's actually number 7. It's going to be z interval. Oops, except I hit t interval. So we'll get to that one tomorrow, next class. So stat, test, z interval. And so in this case, it gives you the option to type it in multiple ways. So like yours will look a little bit different on mine, of course, but there should be somewhere on there where it has a data option and it has a stats option. So stats option is if you know the population standard deviation and you know the sample mean and you know the n. So if you know all those, you can just type them straight in, get your confidence level, and you're good to go. So like, let's see, did I do any that I could test? Let's check. Let's see, so not that one. I was trying to think, did I do one to test? Maybe not. So anyway, but you can try these on your own. So the one I want to do is I want to do the one where we plug in the actual data value. So on mine, I'm going to go to Graph and Calc, and I'm going to use the data. So that way, it's just going to basically do the one var stats for me on my list. So what I first have to do is go into Stat and Edit before I do anything. And I'm going to type everything into list 1. So again, the z interval works good with list 1. So now I need to type in all these values. So I saw a 230. Let's see. 230, 484, 379. Oops, 379. 300, 239. $350, 300. Sorry, I didn't have these typed in earlier, so that would have been a good plan on my part. 395, 230. And finally, 410, 460. All right, so it looks like I've got 11 data points typed in. So let me verify that I really have 11 on my list. So I got 1, 2, 3, 4, 5, 6, 8, 9, 10, 11. So that's perfect. So now all I need to really know is the sigma and the confidence interval that I'm interested in. So I need a sigma of 71 and a confidence interval of 95. And the calculator is going to do all the rest of it for me. So in this case, let me quit out of this, go back to stat, go to test, go to z interval. And so again, I want to be on, so click the data. So notice the only thing it's asking me is what's the sigma. So in this case, 71. What's my confidence level? So type it in as a decimal, so 0.95. And then if I hit test, oops, oh, well, let's see, do I have to do it this way? Let's see. There we go. So now I hit test, pick z interval, and so notice it shows me what the sample mean is. So my sample mean is 343.36363464. My n was 11, which is what we counted. And oh, why is 0.95 up there? A little nervous about that. Well, I'm really nervous about that. Hold on, I must have messed something up here. Hold on. Something's wrong. So 71. So 71. I think you put 0.95. Well, let me try 95. I don't think that's right. See, isn't this so much easier than the other one? Oh, there we go. So now it's on there. So I guess you put in not 0.95. I guess you type in actual 95 in this case. So our confidence level is 95. So our lower bounds in this case would be 301.406 up to 385.321 in this case. And that would be our upper and lower bounds for this Z interval. And if you wanted, you could test it. Let me write down, what is it, 301 and 385. So I'll just kind of round it up for a second. So 301, 385. So we can test this too. So by going back to the calculator and stealing our mean, which was what, 343.36 or 34. So I'll just leave it at 343. It'll be close enough. And so our sigma was 71. Our square root of 11 would be that. And then we're going to multiply this by, theoretically we should multiply it by 1.96. So let's multiply it by 1.96 because that's what the calculator would have done. And so if I multiply 1.96 times 71, I'm doing this on my phone, equals 139.16, then divided by the square root of 11 gives us 41.96, I guess, something like that. So that's going to be our error. So if we add this up, we get 343 plus 41.96, 343 minus 41.96. And granted, I did some rounding, so it won't be exactly what we got on the calculator. Through 343 minus 41.96 equals 301.04, so that's pretty good. And then 343 plus 41.96 is 384.96. So lo and behold, it looks like we did it right on the calculator and we did it right by hand. So again, it's kind of up to you. You can do it either way if you want to use the calculator to do it. I mean, again, the big advantage to using the calculator is you don't have to ever worry about a Z score. So if you have an oddball, like this one, I knew what 95 was, so it wasn't a big deal. But if I had a critical value or a critical value of 92%, then I have to look up the Z-score and all that good stuff. So again, it's up to you if you guys like using that Z interval for this. So remember, it was Z interval. Then go for it. Use Z interval, or if you just like doing it by hand, that's fine too. I mean, Z interval would definitely come in handy for that one problem where you can just go in and easily change the confidence level. Like, so example, if I change this to 90, then how does this change the interval? So in this case, it's what, 308 to 378. So in that case, it's actually gotten a little bit smaller, I think, if I remember correctly. So what happens if we go to like an 80% confidence interval? I don't know why that thing keeps changing on me. Maybe this works better. Oh, maybe I just have to hit enter. I think this will work better on your guys' calculator than it is on this thing, because for some reason this thing seems to be a little wonky at times. Because it seems like I almost have to go out of it to get the right answer. Let's try 99 confidence interval. Okay, so there was a big change. So look at 99 confidence interval. So I think it's backwards of what I said earlier. So notice on the 99% confidence interval, this is a huge interval that we've got now. So our lower is 288, our upper is 398 in this case. So it's allowing a lot more room for error. So what, 288, 398. So if we go back to our 95, $298, I think 398, is that what it was? Let's see. 288 to 398. So that's significantly different than, well, not terrible. I mean, I guess it is off some though. I mean, but it's made it wider. So as our confidence interval increases, our percentage, our interval is going to get wider to kind of ensure that our population mean actually does land in between those two values. So this would have been a 99% confidence interval. So anyway, have fun with this stuff. Like, I've got one for you guys to practice doing the same thing. So again, if you want to get used to using the Z interval, type all that data into list one, plug in your standard deviation, plug in the 95% confidence interval. Again, hopefully it's working better than this weird app. The app seems to be a little funky, even though it does give the right answers after you finally figure out how to use it. And I'll be around all day tomorrow if you guys have any questions or anything. So good luck.